Okay, let's get started. Good morning to those of you in the Americas, good afternoon if you're in Europe, or good evening if you're in the East. I see Jacqueline just joined us from Singapore there. My name is Steve Lewis and I'm a Senior Director of RiskTech based in the UK. Thank you very much for joining us and welcome to this RiskTech webinar. The topic today is about how a robust fire and gas philosophy can help to overcome the challenges of designing a fire and gas detection system. Hopefully we can provide some useful and practical insights for you. Before we get going, the usual bit of housekeeping. We've muted everybody so the sound won't be distorted by background noise. So if you'd like to ask questions, and we really do encourage you to ask questions, we set some time at the end to cover them, please use the instant messaging function. So that means if you just click on that little white speech bubble in the bottom left-hand corner of your screen, type the message in, I'll keep track of these, and we're aiming to cover as many of them as we can at the end of the session and within the sort of 40-45 minutes we've got available today. Okay, so for those of you who don't know RiskTech, I'd just quickly like to introduce RiskTech. So we've got over 300 people across 16 offices worldwide. We're part of TUV Rhineland, which is a €2 billion provider of technical services, including testing, inspection and certification. Our main business line is consulting, where we provide a range of specialist risk and safety management services which help to reduce and manage risk for our clients. We also provide online and classroom training, including postgraduate education up to MSc level. We also provide resources in terms of associates who are able to work at client locations to help fill any specific resource or skill shortages. We also offer and deliver industrial and integrity management services, and also we undertake research and development activities in the field of risk and safety management. Okay, so I'd just like to introduce our speaker today, John Wiseman. John is a principal engineer based in our Warrington office here in the UK. He has over 14 years of quite varied risk management and technical safety engineering experience. That covers a number of high hazard industries, including oil and gas, civil nuclear and defence. Okay, John, over to you.
Okay. Thank you, Steve. So as Steve said, my name is John Wiseman, and firstly I'd just like to thank everyone for taking the time to listen in on this webinar. I really hope you find it interesting and well worth your time. Okay, so as Steve said, today I'm going to be talking about the main considerations that need to go into the development of a fire and gas detection philosophy. So I'm not going to talk about the exact contents of these documents, but I am going to cover the main elements and the main process we must go through in both developing a fire and gas detection philosophy and implementation of a fire and gas detection system. So as we know, during the design stage of projects, many different types of philosophy or design basis type documents are developed, and this is primarily to assist the project as it progresses further into design. However, of these philosophy type documents, perhaps the fire and gas detection philosophy is one of the more contentious or well debated documents. So those involved in fire and gas detection design will be well aware that there are many different opinions and many different solutions in the way that these systems are implemented. So with this, the fire and gas detection system design has a number of challenges. So the main challenges, I'm just going to go over them now. The first one, so I'm talking about outside process areas here. So the first challenge, that implementation of a fire and gas detection, what we see when we're implementing a fire and gas detection system, is the lack of publicly available guidance. So whilst guidance does exist for indoor locations, so for example here I'm showing NFPA 72, this is mainly a prescriptive approach and is more suited for indoor locations where we have more of an understanding and the behaviour of the hazard is more predictable. We know it's going to be contained within the building itself. So a fire detection system, for example indoors, can follow a more prescriptive regime. Another reason why fire and gas detection systems are difficult to design for outside process areas is sort of conversely to the first point there, is that there can be an overload of information to the designer. So there are many different types of detectors out there, different types of technologies, each of which come with their own specific data sheets. And whilst these data sheets are useful for the individual detectors, they don't shed very much light on how they should be integrated into the overall detection solution. Another reason why fire and gas detection design can be a challenge, and perhaps the main reason why historical performance of these systems has been relatively poor, is due to the variability of the hazard outcome. So if we take a process facility, for example, we have many different link locations, release points across the facility, then the release directions, the different sizes of release, and then there are the external factors such as, for example, the speed of the wind and the direction of the wind, and if the release is flammable, whether or not it hits an ignition source. So all of these different inputs kind of factor together to give us an unmanageable range of scenarios for which we must design our fire and gas detection system against. Another reason why it can be a challenge is due to the range of different types of facilities in which these systems are installed. So taking the two extreme examples there, we've got the onshore facilities where we've got more space, evacuation routes, we have more space for those. Muster points can be located further away from the process areas, and we can also separate process units away from each other. And also for onshore facilities, it's typically more chemical processing, or it can be more chemical processing, and in which, if that's the case, we might want to have a more controlled shutdown of our facility. Whereas offshore, we've got much less space, the equipment is much more congested, people are working much more frequently in and around the equipment, they also live near the equipment, and with the congestion, there is also much more of a kind of an explosion hazard associated with that can quickly affect people. So for example, on an offshore facility, our fire and gas detection system may need to be much more quick acting with an automated response to shut down. And then finally, we've got the different types of hazard that our detectors must detect. So we've got the flammable gas hazard, we've got the toxic gas hazard, and then if the release is flammable and it ignites, we've also got the fire hazard, and we must install detectors that are capable of detecting all these different types of hazard. Okay, so that's the main challenges we face when implementing a fire and gas detection system. But before I go into the methodology, I just want to go over kind of the limitation and the role that fire and gas detection plays. So I think it's it's important to understand that the detection system itself does not actually reduce the risks. It must successfully interface with the subsequent steps. So as shown here, the detection system must flow into the decision step, whether that's automated logic or an operator making a decision. And also from that, we must then take appropriate action coming out of that. So in its own right, the detection system does not reduce risks. It must form part of this chain, if you like, for the actual risks to be reduced. Another important point is that fire and gas detection system is a mitigation system. So if we take a bow tie diagram, for example, if you know about those, if the top event in the middle, if that's loss of containment, the fire and gas detection system typically resides on the right hand side. It's a risk mitigation system, and because it's there to kind of mitigate the hazard as it's already lost containment, its performance in terms of risk reduction is much more uncertain, and because of that our efforts might be much better placed if we place effort into implementing maybe a more robust maintenance strategy, or installing maybe more process control and monitoring equipment to prevent the loss of containment in the first place. And it may be that from these prevention measures we could create the argument that the risks are already sufficiently low such that fire and gas detection system is not needed. But for most process facilities that would actually be a difficult argument to make, and the fire and gas detection system forms a crucial part of the overall safety argument for a facility. So the main objectives of a fire and gas detection system, so I have just touched on these, so I'll just quickly go over them. Obviously it must detect, and it must detect the hazard once it's lost containment quickly, in order to minimise the immediate consequences and prevent escalation. It must then go on to alert the operator at a control panel or personnel located in the field, so they can take appropriate action and maybe evacuate from the area, or an operator at a control panel can take appropriate action, perhaps to shut down the facility. And it must also, coming out of that, there must be action initiated either manually by an operator or automatically by the control logic, and that action must mitigate the consequences to minimise escalation and reduce overall loss. So that might be something like isolation to limit the potential inventory that could be released, or active fire protection, for example. So now we understand kind of the key objectives and limitations of the fire and gas detection system. What are the key stages we should really go through to develop a fire and gas detection philosophy? So understandably, there is a critical link to the hazard and risk assessment. So in order to understand the specific requirements on our fire and gas detection system, we must first understand the level of risk, the main risk contributors, and we must appreciate the risks to asset, personnel, and the environmental risk. So understanding the risks enables us to kind of extend the general system objectives that I've just discussed into more specific, facility-specific requirements on the fire and gas detection system. And once we have defined these requirements, we are then in a position to choose the right technology that satisfies these requirements and is also suitable for the hazard that is actually being detected. Following on from that, or very much in tandem with choosing the right technology, as we shall see, we must choose an appropriate layout strategy that effectively mitigates the main risk contributors. Once we have our layout strategy and our detectors positioned throughout the facility in accordance with that strategy, we are then in a position to assess its performance. Now there are a number of performance assessment techniques that I'll discuss in more detail later, but it may be that assessment reveals weaknesses in the system, or it doesn't achieve certain criteria, and in which case we may well have to go back to choosing more appropriate technology, more reliable technology, for example, and then going on to positioning our detectors throughout the facility. But if we do satisfy the criteria and we successfully get through this step, we are then in a position to install, commission and operate our facility. And throughout these phases we must continually review the performance of our system and also review our system in case there are any sort of process changes or any changes to the layout of the facility, and in which case that will likely require us to go right back to hazard assessment and redefining our the requirements on the system. So I'm just going to go through these steps in a little bit more detail now. So the first step is hazard assessment. So as a risk mitigation system, the fire and gas detection system should have very close links to the risk assessment. And as we know, there are a wide range of techniques for assessing hazards, from qualitative assessment using hazard checklists or checklist type approaches to more quantitative assessment techniques that may use dispersion analysis or even computational fluid dynamics. One effective method to visualize the potential outcomes from a release scenario, though, is through use of an event tree. So you may well know that this is primarily used as a quantitative assessment technique. However, as you can see here, it does allow us to visualize the potential outcomes from a release and how we may then go on, and which outcomes we may then go on to design our fire and gas detection system for. But as I said previously, the number of outcomes can be unmanageable, and if that's the case, then it may be that we want to apply frequencies or probabilities or even just weightings to these steps through the event tree. And that will enable us to prioritize or find out what the highest frequency outcomes are, those that are contributing most to our risk. And from that, we can then tailor our fire and gas detection system to the more dominant risk contributors. Another approach, and one which is actually very useful for fire and gas detection system, is more of a simplistic checklist type approach, where we review the material properties, its pressure, its temperature, whether it's toxic, for example, the nature of the release, and also the nature of the release in the environment. So, for example, is the release going to be into a congested environment, or there are any congested environments in the vicinity of the release, and in which case we may have more of an explosion hazard, and that might be what we are the dominant risk contributor, and that's what we may design our fire and gas detection system for. Other things that may affect the release, the topography of the site, any dominant wind directions will heavily influence the positioning of our gas detectors. And then, of course, whether or not there are any ignition sources that enable us to prioritize where our fire detection goes. So these are kind of two proposed approaches, but of course, for most facilities or most complex facilities or bigger facilities, analysis is already undertaken as a matter of course. So we may already have a quantitative risk assessment or more consequence-based assessment through computational fluid dynamics. And if those have been undertaken for our facility, then we can use the results of those as input to our hazard assessment for our fire and gas detection system. So once we've performed the hazard assessment, from that we must define specific requirements that serve to reduce the risks as much as possible. So there are a number of requirements we can place on the fire and gas detection system. I've listed a few here. This is by no means comprehensive. So, for example, we may wish to specify a specific response time, and this is primarily determined by the speed with which consequences could escalate. So, for example, if it's a congested area and we have an explosion risk, we may we typically need fast-acting detectors, and equally, if the detectors are in ventilation, we need that to be fast-acting there. So dampers are closed. Other requirements include the alarm levels. Again, this is very much tied to the speed of a response, but we've just got to be careful that with lower alarm levels, yes, we do get quicker response, but we also are more susceptible to false alarms. So it's a balance. The size of the hazard we want to detect, which is driven by the proximity of equipment and whether there's any nearby equipment that could escalate the situation. Coverage requirements, the reliability of the equipment and its maintainability, and how the maintainability is driven by how easily accessible the detectors are throughout the facility. The voting logic arrangements, so if we require a reliable signal to shut down, then we may choose to vote shut down, for example, on at least 2 detectors giving us a signal. Survivability requirements, and then as I discussed previously, the interface requirements and the interface with the control logic and the final action. So that's just a number of requirements on our fire and gas detection system. But one thing that's important is that these requirements must have a clear pass-fail criteria, so the performance can be clearly assessed or tested. So by that I mean usually it's good to assign numbers to things. So for example, we may have a detector response time of within 10 seconds, and that just enables us to demonstrate that more clearly that we are achieving that particular requirement. So once we've determined our requirements that reduce the risks, we are then in a position to choose the technology. I'm not going to go over the different types of technology here, but the technology of choice must both serve to reduce the risks, but also it must also be suitable for the environment it's being operated in. So we need to take into consideration potential contaminants. Is there dust in the area, sand, the environmental conditions? So is the equipment the detector being attached to, does it have high vibration? What are the background noise levels, particularly for acoustic detectors? And the feasibility of the installation. Is there too much blockage, for example, for flame detectors? The maintenance burden, so do we have to continually calibrate the equipment? And of course another consideration might be the certification of the equipment. So the detector itself doesn't become, for example, an ignition source in a classified area. Once we've chosen our technology, or very much in tandem with choosing the technology, we must also choose an appropriate layout strategy. Now, there are a number of layout strategies proposed in the CCPS book, Continuous Monitoring for Hazardous Material Releases. So I'm just going to go over these now. So we've got volumetric monitoring, and this type of detector layout is primarily for protection against explosion hazards. So with this arrangement, we are looking to achieve a certain density of detectors throughout predefined volumes, such that a cloud size cannot develop such that if it was ignited, we would end up with a damaging overpressure. So that's very much ensuring we have a sufficient density or an array of detectors throughout a volume. Another layout strategy is enclosure monitoring, and this is very much specifically for protection of buildings, both positioning of detectors within buildings and also at any ingress routes to the buildings, so for example through any sort of ventilation routes into the building. Another layout strategy is source monitoring. So this is more associated with protection of detection of leaks from specific leak sources themselves. So for this layout strategy, we might need to have more of an understanding of the nature of the release. So for example, we might support any sort of layout we did based on this strategy with consequence modeling, because we need to understand the behavior of the release a bit more for this particular layout. We also have target receptor monitoring. Now this is very much positioning of detectors in locations of vulnerability. So that might be, for example, occupied areas or routes through our facility where people walk or congregate. So this detector layout strategy is very suitable for toxic detection, where we have a direct threat to personnel and we need to know whether there's a toxic hazard in areas where people are located. And then the final layout strategy is perimeter monitoring, and this is mainly for protection against gas migration to vulnerable locations. So this might be perimeter monitoring around a process area, so we know when we've got a gas leak that's migrating away. But also we may choose to put perimeter monitoring around a vulnerable area. So for example, at the boundary of a site where we could potentially get a migrating gas to a public area, or if we have an area of facility where there's a non-EX rated equipment, we may wish to put perimeter detection around that so we can shut down the equipment. Okay, so once we've defined our layout strategy, we are then, and from that we've positioned our detectors throughout the facility, we are then in a position to assess performance. So I'm not going to go into great detail about the different sort of performance techniques, but I'm just going to touch on fire and gas mapping. So there are two quantitative approaches to fire and gas mapping, and fire and gas mapping is used to verify the coverage across our facility. And there are two approaches. There is geographic mapping, which is associated with determining the fraction of the volume in our process area that we are detecting that is covered by detectors. And then there is also scenario-based mapping, which is a means of determining the fraction of the release scenarios to be detected. Now, I'm not going to go into too much detail on fire and gas mapping. Each of these techniques have their own pros and cons. It's very hot topic at the moment, as debated as to which is the best technique. But what I will say is that each of these techniques have their own sort of areas of suitability. So, for example, geographic mapping is more suited to placement of detectors where we've got an explosion hazard, a congested, for example, a congested volume, and we need to demonstrate that a certain cloud size can be detected by the detector arrangement, whereas scenario-based mapping may be more suitable for onshore process areas, where geographic mapping may lead to too many detectors, and we need to kind of understand the nature of the release a bit more. So geographic mapping is a more simplistic, perhaps a simplistic approach, where we're considering the geometry of the area, whereas scenario-based mapping, we're actually assessing the behavior of the dispersion against specific release scenarios. Okay, so that last point there, as I've said, the mapping technique should complement the detection requirements, and in particular the layout strategy. One further note on fire and gas mapping. So at RiskTech we do a lot of fire and gas mapping, but all too often what we find is that the initial steps have not really been completed, and there is this tendency to go straight to the fire and gas mapping exercise in the hope that it will provide you with the optimum solution. But this isn't the case. The way we find the best fire and gas detection solution is through going through these initial steps, through going through the hazard assessment process and choosing the right technology. And fire and gas mapping should really be used as a performance assessment technique, a verification technique. If it's suitable. So for example, where the layout strategy is prescriptive, such as for example in buildings or in air intakes, fire and gas mapping is not appropriate for those layout strategies. And then finally, if we satisfy the requirements. We then go through the process of installing and commissioning our system, and going into the operational phase. And throughout these phases, we must continually review the system performance. As I said, the features of the facility may change, the process might change, which in turn means we need to go back to assessing the hazards and redefining the requirements. If there are any changes as a result of this to the fire and gas detection system, it must be controlled through a management of change process. And then if our fire and gas detection system is designated as a safety and environmentally critical element, then we will need to bring in an independent competent authority to review the system. Okay, so I've quickly gone over a proposed methodology there for designing or developing a fire and gas detection philosophy. So in summary, implementation of fire and gas detection system is a challenge, and performance historically of these systems hasn't been great. This can be put down to perhaps the lack of guidance and the difficulty in choosing which hazard or which outcome we are designing our system against. And so to counteract these challenges, it's important that every project or facility has a fire and gas detection philosophy in place, so there is an agreed basis on which to design the fire and gas detection system. Having this in place ultimately ensures that the risks are reduced in an effective way, and we can all be confident that our system is performing for the main risks at our site. Ultimately, this will improve, having this structured approach hopefully will improve the safety at our facilities. Okay, so that's the end of the presentation. So yep, now it's time for questions and answers. Steve, have any questions?
Yep. Okay, so thanks very much there, John. Yeah, we do have, we've got a good sort of 10 minutes. If we have any questions, I say we've got one question. Normally we get lots and lots of questions, so either you've been 100% crystal clear, John, or I think so we encourage people, if you do have a question, put it in there. But anyway, we have a question to get us going from Howard. There is a variance in fire and gas philosophies across UK operators, where a high level gas detection, so that's gas detection, will activate the deluge in that area, where others will not initiate deluge. Is there any current design criteria that would dictate which, if one or the other philosophy, should be adopted?
So currently, I'm not aware of any design standard for that kind of specific requirement. I think what I would say is that we need to put it through the process, really, assess our risks, and also consider the speed at which we need to initiate that response. So yeah, just kind of put it through the risk assessment process, and as long as it's documented and everyone can review, then we can implement the system for that particular scenario.
Okay, thank you. Question from Jacqueline. Is there any source of information to further understand survivability requirements?
So survivability requirements is a very specific thing. So typically for fire and gas detection systems, if the detector head, if you like, is damaged, then that by default goes to an alarm signal. So on that basis, because it's kind of fail-safe, if you like, there are no specific survivability requirements, but we need to consider both normal operations, the environment it's operating in, is it suitably protected from the conditions, but also, it may be that we have a specific survivability requirement on the detector, and in which case we might need to design a bespoke solution against that hazard.
Okay, thanks, John. Just as we're waiting for some other questions in, I had a couple of questions that occurred to me. I think a lot of participants, perhaps on this webinar, are going to be familiar with fire consequence modelling, sort of gas dispersion modelling, but perhaps a little less familiar with fire and gas mapping. So can you explain the difference between the two?
So, the fire and gas mapping is primarily a kind of a performance assessment technique. So we first have to determine the coverage requirements of our system. So and the coverage requirements are primarily determined from the probability of detection. So the fire and gas mapping basically ensures that we have a sufficient number of detectors throughout our process area, so we have a high probability of detecting the hazard. So yeah, is that your question, Steve?
Yeah, I was going to say, I think people are probably quite familiar perhaps with running physical effects models for certain releases of certain hole sizes and so on.
Yeah.
If they were doing perhaps as part of a quantitative risk assessment. But then how would you contrast that with the fire and gas mapping study where you're deciding where to place detectors?
So I mean, the physical effects modelling. So as I said, there are two methods of mapping. There is the geographic mapping, and then there is the scenario-based mapping. So the physical effects modelling or the dispersion analysis is very much used in the scenario-based mapping approach, where we need to understand the nature of the specific releases, and we need to know where they are, or where the hazard is going to be located throughout the facility, and we may have a particular target on the system, such that a certain fraction of detectors see the hazard. So the scenario-based mapping approach is very much dependent on physical effects modelling and understanding the physics of the release, whereas the geographic method is a much more is a more simplistic approach, but that doesn't mean it's any less useful. It's just a different approach for a different type of area, if you like. So it's typically used in congested areas, where we have a volume of, where we take we idealize the hazard for geographic mapping, a spherical hazard. So we typically use a spherical gas cloud. So it's very much so the geographic mapping approach is very much a geometric exercise with a spherical gas cloud that is mapped throughout the area.
Great, yeah. Yeah, great. Thanks for the explanation, which leads very nicely onto a question from Elizabeth. Which software are used to do geographic mapping?
Well, there's commercially available software. There's the likes of Detect 3D or Hazmap 3D. However, many consultancies, including Ristec, develop their own in-house software. So this this software incorporates ray tracing techniques, for flame mapping, for example, where we need to fully understand the blockage in the area. So yeah, I mean, there is commercially available software, but there is very much the underlying calculations, if you like, can be performed using in-house software as well. So yeah, Ristec we have our own in-house software that we use on a lot of our consultancy on a lot of our projects. Yeah.
Okay, thank you. Question from Ilaria about perimeter monitoring. Which is the best approach you suggest in terms of their deployment? Some clients are quite reluctant to use them for the difficulty of alignment and high risk of spurious alarming.
Okay, so I guess it's coming back to the question of what are the risks at the facility. If there are areas outside the process area that are particularly vulnerable, then if that's the case, then yes, the best means of achieving perimeter monitoring is through line of sight detection. But line as in the question, line of sight detection can have operational issues, so it is susceptible to false alarms through if there are any environmental effects such as dust or steam, for example, that can cause false alarms. There are also operational issues, if it's when people walk through the area, the line of sight needs to be above any walking routes like that. But in terms of misalignment, I think we've got to ensure that the foundations on which the detector, the transmitter, and the receiver is ensure the foundations is robust. Don't go attaching the detector to equipment that vibrates a lot, for example, that can cause misalignment. But also, maybe not use the full path length. So a lot of vendors quote a range of 120 meters between the transmitter and the receiver, and of course if we increase that distance we're much more susceptible to misalignment. So minimizing the path length as well between transmitter and receiver can reduce the potential for misalignment. So ensuring we've got robust foundations and perhaps reducing the path length. So some standards actually limit that path length. So although the vendors are quoting 120 meters, some standards recommend not going above 60 meters.
Okay, thanks, John. We've got two more questions, which we'll just get through these quite quickly then. Question from Jagan. In some latest LNG projects, there are requirements to design the safety critical equipment to withstand the potential blast overpressure. Is it a standard approach to design fire and gas devices to withstand the blast overpressure?
The thing is with that, if we that's kind of the incident has already occurred at that stage, but as I said earlier, it's typical for detectors, if they are damaged, to go into an alarm state. So on that basis, if they are damaged, we do have an alarm at the control panel, or at least we have a signal at the control panel. So yeah, typically we don't have kind of overpressure withstand requirements on detectors. However, having said that, there may be specific requirements on the project, and in which case we might have to think about protecting the detector in some way. But usually, if an explosion has occurred, that's after the requirement for detection.
Yeah, and then the final question was from Chris, who in his sort of introduction to the question pretty much said what you said, but his final point was, are there any events would you say that are worth considering for survivability criteria, recognizing that the explosion has already occurred?
So from my experience, I haven't ever come across a situation where that might be the case. However, I'd be interested to hear actually if there are any particular design requirements for that, what the particular situation is in hand. So yeah, I'd be more than happy to get into discussion about that, about the specific survivability requirements on that project.
Okay, great. That's great, John. And people can contact you via your email address, which is in the presentation. We will be making a recording available to everybody. That'll probably be early next week now. So if we just pop up the final slide, please, John. Yeah, so if you have any other questions arising from what you've heard today, you would like any information on our services, then just simply email us. There's a couple of email addresses there on this current slide. Or, of course, you can just go to our website, risktech.tuv.com, and there are a ton of forms on there where you can just fill in, get contact with us, and we'll get back to you. So thank you again, John, and thank you everybody for your attention. We really do appreciate you taking the time out today to listen to us. So that wraps it up for today. The next webinar, I believe, is on Thursday. So stay safe and stay secure. Goodbye.